Let's take a look at section 4.3, and the name of the section is Riemann sums and definite integrals. We're going to build basically on what we talked about in the last section. We talked about area under a curve. I'm going to try to put that together with stuff we did earlier in the chapter with the integration. And so remember that when we find the area under a curve using rectangles, what we're really finding is called the Riemann sum. I don't know if I actually used that term yesterday, and it's not a big deal, not even a huge deal that you remember that that's what it's called, but it's named after a German mathematician named Riemann. And the width of a rectangle, if we think of the width of each rectangle as the subinterval, and we think about the entire partition, or the entire interval rather, as the partition. The subintervals don't have to be the same size, although we generally make them the same size for simplicity. However, if they're not the same size and we think about the length of the longest subinterval, which we call the norm, and we denote that using, if the partition, the entire interval is called P, then the norm, or the length of the longest subinterval, is the symbol of P. And what I want you to think about is that as the norm gets smaller, so in other words, as the rectangle with the largest width or the largest length gets smaller, the approximation for the area gets better. And the reason is because that's going to force the number of rectangles to increase so that it fills the space. If we put this together, this is the same thing we had in the previous lesson. So remember that sigma we had, the sigma from 1 to n. F of x sub I, remember, was the height of each rectangle. Delta x sub I was the width of each rectangle. The difference is now, instead of taking n to infinity, we're using this norm goes to 0. It's the same thing. I don't want you to get too caught up in the notation here. Worry about all these little parts of the notation. When we did this the other day, we wrote this using this notation, the limit as n approaches infinity. But it's the same thing, whether they use this norm goes to 0 or n goes to infinity. These mean the exact same thing. These mean we're adding up those rectangles to fill that space so we can approximate the area under the curve. Leibniz, so this other mathematician, and Leibniz we've heard before, anytime we use dy dx notation, that's Leibniz notation. He came up with a better symbol, or a more simplified way of writing this notation. Instead of writing the sigma every time, he used the integral symbol. So remember the integral symbol we had earlier in the chapter. He went back and he said, okay, let's call this the integral of the function on the interval from a to b. So let's break this notation down a little bit. So the integral symbol, of course, we know what that is. The lower limit of integration would be a, so that's the left endpoint. The upper limit of integration would be b. We would call f of x, whatever function we're working with, the integrand. And of course, dx means we're doing the integral with respect to x. We sometimes call this a dummy variable, and I'll explain that later in the chapter, but that's the variable of integration that we're working with. It says it's called the dummy variable because it doesn't matter whether you use x, t, whatever, it's still going to give us the same area under the curve. So we have this notation for integration, but we still need to learn how to evaluate the integral. And we'll talk more about how to evaluate the integral as we go through this chapter. For now, we're going to continue to use those limits and those rectangles that we talked about in the previous lesson. A little vocabulary: if the integral can be integrated, that means we call it integrable, which is kind of a funny word. As long as a function is continuous, that implies that it's integrable, or integrability. So as long as we have continuity, we can find an integral, or we can integrate under the curve to get the area under the curve from a to b. So let's do a quick example here. If I wanted to find the integral from -2 to 1 of the function 2x dx. So this is continuous, of course, over all real numbers, so we know it's integrable so that we can work with it on that interval. So we're going to set this up using that 5-step process we used in the last lesson. So remember, the width of each integral, or the width of each rectangle rather, is b minus a over n. So in this example, that's 1 minus -2 over n, or 3 over n. And you don't have to write all this, but if we kind of built and did step-by-step increments so that we could get the x sub I. Remember, x sub I was given by a, the left endpoint, plus the width, 3 over n, times I. And they're just pointing out that if you took this all the way to n, notice that that gives you our upper bound. Don't worry about all this. Just use that 5-step process we used the other day. So this is the notation you might see in the textbook. This is the notation we used the other day. If we put all of this together, though, remember what we did. We put the x sub I expression in place of the x for our function. Remember what our function was. Our function was 2x. So in place of the x, I'm putting this x sub I expression times the width of each rectangle, 3 over n. We're going to take the summation from 1 to n, and then we're going to take the limit as n goes to infinity. So remember all those summation rules we talked about. We're going to simplify this just a little bit. 2 times 3 over n, I can treat that as a constant and put that in the front. Summation rules, -2 is a constant, so that turns into -2n. 3 over n is a constant, and remember the sigma for I from our rules from the other day for summation becomes n times n plus 1 all over 2. So if I do a little algebra and clean this up, I get this expression. Now take the limit as n approaches infinity. We get -12 plus 9 because the degrees here are the same, which leaves me with -3. So our integral for the original function was -3. Now, one thing I want you to observe is that this is negative. So if I asked you for the area under the curve over the interval, we would say it's a positive area. But in terms of integrals, we can have a negative integral. What do you think that means graphically about what's happening? So we'll talk about this a little bit more in class, but if we draw a picture, we'll see that part of the graph is under the x-axis. Let's do another example. Evaluate the integral from -1 to 1 of the function 3x squared plus 2. So the width of each interval is b minus a over n, which in this case is 2 over n. Again, you don't have to write all this out. Just give me your x sub I expression. So remember that it's a times the width, or plus the width times I. Put that into your expression for your sigma. So we get, since the function was 3x squared plus 2, we get 3 times that x sub I expression squared plus 2 times the width, 2 over n. Do a little algebra here. I brought the 2 over n to the front. We can take some time in class and go over this algebra a little bit more in depth. Just go with me for now. Make sure you remember the rules for summation. If we separate all of this and simplify using our summation formulas, take the limit, remember, as n goes to infinity, and we get a value of 6. And again, I know I'm going through this kind of quickly. We can go through the details in class a little bit more in depth, but I want you to remember the process. The main takeaway from this lesson is that when you see this expression and they ask you to integrate over a given interval, we're basically back to using the summation formula. And that's what Riemann and Leibniz worked together. They didn't really work together, but they came up with these expressions. As long as f is continuous and non-negative on a closed interval, then the area of the region bounded by the graph of f, the x-axis, and the lines from a to b is given by this function. Okay, so we can also use this to find area. So example 3 says, write the integral that represents the area under the curve from 0 to 4 for this particular function. Okay, so what this little rule here says is that we can express this using an integral. So it's going to be the integral of the function from a to b, which is 0 to 4 in this example. And that's it. And if we wanted to actually compute this, we'd go back and use that limit process that we talked about a few minutes ago.